I can't express how satisfied I'm right now because I was just randomly trying to use the matrix expression for Fibonacci numbers to prove different formulas, right? Especially after I found in like my previous two videos that we can prove this formula f of n plus 1 n minus 1 Fibonacci number minus f and Fibonacci number square, this product, is equals to minus 1 to the power n. After I found that this can be proved using the matrix representation for Fibonacci numbers, fn plus 1, this one, so this matrix is equals to 1 1 1 0 to the power n. So in our last two videos, we explored this in depth. We also proved this and we also analyzed this, right? After I found this formula, after I found that this can be proved by just using this matrix formula and then taking the determinant of this matrix on both sides, I was trying to use this to prove other formulas too. And for this formula also it worked. Like this worked. We can prove this using this formula. And when I proved, I was really happy. And yeah, now I want to share with you like how my happiness, right? Now let's do it. So if f and v have b and Fibonacci number, we need to prove this, right? Now, first of all, we have defined this. This is if you want proof of this, please go to my previous videos and you can find the proof there. So from here, we see that if there's fi over here in this matrix, and over here if it's fi minus 1, if over here it's fi plus 1, this will be equals to 1 1 1 0 to the power I. Right, now over here there's also this thing called, now what I will try to do is basically I will try to sum this thing I equals to 0 to n of this matrix, f I plus 1 fi 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 minus 1. I will try to sum this matrix, and we know that basically if sum the matrix is the same way as summing the individual elements, right? So sum from I equals to 1 to n of fi plus 1, sum from I equals to 1 of fi, sum from I equals to 0 to n of fi, and sum from I equals to 0 to n of fi minus 1. And yeah, this is same as this. And so from the result, I can basically compare the second element or third element and get the required expression, right? Now over here you might argue that f of minus 1 is not defined, but yeah, but it's defined actually. Like using the definition that Fibonacci number is f n minus 1 plus f n minus 2, and the fact that f of 0 is equals to 0, f of 1 is equals to 1. Using this fact, we can get the terms in the right side, right? 0 plus 1 1 2 3. So we can also get the term in this side, because we know that these two should sum up to 1, this should be 1, right? So that these two sum will be 1. Now again, this two now there should be two numbers, so we sum to 0, right? So this will be minus 1. Again, there should be two numbers, we sum to 1, so this will be 2. So that 2 minus 1 is 1. Now that should be minus 3. So you see that all of these numbers are defined, so f of minus 1 is defined, so this is completely fine to do. Now let's try to sum this up. Sum from I equals to 0 to n. We know that this is just 1 1 1 1 0 to the power n, right? Now try to see matrix as a number. We know that if we have sum from I equals to 0 to n of a to the power n, this is just the first term. Let's say this is x to the power n. Now then we see the first term first. The formula is a r to the power n minus 1 by r minus 1, where a is first term and r is common ratio, right? Here first term is 1, x to the power 0 is 1, ratio is x to the power n minus 1 by x minus 1, right? Similar process we will use here. First term is just 1 1 1, sorry, first term is this matrix to the power 0, right? So that will be 1 in matrix form is this thing 1 0 0 1, right? This is the 1 for matrix A, and our R will be that matrix itself, R to the power n. How many terms are there? N plus 1 terms are there, right? Okay, so over here if it goes from 0 to 1, there should be n plus 1 terms. I'm sorry for that. A R to the power n minus 1, again 1 is 1 0 0 1. Okay, A R to the power n minus 1 by R minus 1. Again R is 1 1 1 0 minus A R to the power n minus 1 R minus 1. 1 again 1 0 0 1, right? I was just trying this. I haven't really, I wasn't, I'm not really sure like if this is valid or not, but I just thought of, yeah, why not to try? Why don't you just look at the matrix as simple numbers and use the matrix form? Yeah, and I thought, oh yeah, maybe it will be fine, and you did this. Now we know that this will just be 1 0 0 1, and then now for this one we cannot really do anything right now. Yeah, but we know that this will, we know this matrix actually, there will be n plus 2 Fibonacci number over here, n plus 1 Fibonacci number. Yeah, we know that, right? Okay, but we will do that later on. To the power n plus 1 minus 1 0 0 1 divided by, now if you subtract this 0 1 1 minus 1, right? And after that, if you take it to the numerator, that will be inverse, right? So, and this identity matrix will just multiply other matrix to give the same. So I don't think we need to write this, but let me still do that. 1 1 1 0 to the power n plus 1 minus 1 0 0 1, and if I take its inverse, 1 by determinant is just minus 1, right? And then over here I have to interchange these two, minus 1 0, and again negate the other ones, right? Now this minus 1 can be used to multiply these terms over here, right? And I know that A times a matrix is that this A will multiply the entire terms, right? So if minus 1 is multiply this entire thing, that will just go, right? Okay, now after this, what you can notice is, if you, this is same as this number over here, so this is actually 1 0 0 1 times over here we will have 1 1 1 0 to the power n plus 2 minus, since this identity matrix times anything will just be that anything, right? And also since this is identity matrix, if it will multiply these two, that will be same, it will not change, right? Minus 1 1 1 0. Now we know that this matrix will just be f of n plus 3. This is also from how like we, from this formula itself, this from this formula over here. Now this will be f of n plus 3, f of n plus 2, f of n plus 2, f of n plus 1 minus, now over here this is basically I can write this as f of f1 f0 f2 f1. You can identify this if you had gone through my previous videos, right? Now this is just f n plus 3 minus f2 f n plus 2 minus f1, or also I can write 1. Anyways, that's gonna work, I'm just making it more systematic. F n plus 2 minus f1 f n plus 1 minus f0. So we got this result. And what is this result for? This is for this sum, right? Sum from I equals to 0 to n of f I plus 1 fi 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 minus 1, right? So from here And I also told you that this sum actually can go inside, right? This sum will eventually go inside. So from here, if we compare these two, we can clearly see that if we take the second element, sum from n equals to 0 to, sorry, sum from I equals to 0 to n of fi, and if we take this, will just be f n plus 2 minus 1. And this is a really beautiful proof of this formula. We can easily prove this using induction as well, but this proof, I was so surprised when it worked. Like I wasn't sure if it would work. Yeah, but then when I saw that it works, I was so surprised. And yeah, now I think if you hadn't known that this works, you would also be surprised, and I think you are also satisfied with this, right? Okay, this is it. Thanks for watching. Look forward to seeing you in the upcoming videos too.